We are going to continue pretty much right where we left off, and we're going to start talking about work function differences between the metal and the semiconductor of a MOS device. So we're going to look at the entire MOS system, and we're going to look at all the energy levels, because again, that's my favorite thing to do. So we start off in the metal, and you will notice that between the vacuum level at the top, which is there as a reference basically, there is a metal work function, and that's something we can actually go look up. We've looked up that before. And that's just the difference between the Fermi energy in the metal and the vacuum level, which is, again, a reference level. In the silicon dioxide, which is in the middle, we have a affinity that goes between the vacuum level and the conduction energy, and then the distance between the conduction energy and the valence energy is really, really far, which means that the valence energy is basically going to drop off the diagram when those are put together, because that's a really, really big value. So the band gap being 9 electron volts means that there's actually quite a bit of distance there. And then in the silicon, we have p-type silicon, so the Fermi level is down near the valence band, and there is an electron affinity value, chi, which you can, again, look up, and those are kind of the things that we are going to be putting together. So it gets brought together, and what's going to happen is the Fermi level is going to have to be constant throughout the system. So something's going to have to move, and that's going to be the semiconductor, so that the Fermi level can be constant. And also in the oxide, there's going to be a voltage drop. So there's actually going to be a drop in the conduction band between the oxide and the metal. So the bands in the semiconductor side are going to have to bend, because they're going to have to adjust for the fact that you have to keep that same relationship between the intrinsic and the Fermi and the valence and the conduction at the bulk material, and then they will bend in order to accommodate what's going on with the Fermi energy at the surface. So we've talked about that when we talked about the oxide and semiconductor connection before. So there's a potential drop across the oxide, like I said, and so the vacuum level actually moves a certain distance, and we're going to look at that distance that it dropped, or that voltage drop across there, in a minute. The standard things that we have to stay in place. So in other words, the constants that were associated with the three types of materials when we went into this has to stay. So the value of the work functions in the oxide, the chi value for the oxide, the work function of the metal, and the chi function for the semiconductor material, the work function for the bulk material, and then the band gap between the conduction energy and the Fermi intrinsic energy is going to be about half the actual whole band gap. Those constants all have to stay the same, and this is why the bands have to bend, because chi has to have the same distance at the interface between the vacuum level and the conduction energy, so that's why the conduction energy is bent, because the Fermi level was pushing it up, and then it has to bend down to accommodate. So those values are all the same as they were before the materials were connected. So we're just going to gray those out for a minute, because those things we know. And then there's a couple things that are new. One is the voltage drop, or drop in potential energy, between the metal and the oxide. And this is generally, if it's represented as an energy right now. That's what all those little E's in front of those values mean. It just means that those are in joules. And if we divide everything by the charge of an electron, they'll all be in volts. So if you see the value have an E or not have an E, don't worry about it. We just usually on energy diagrams, because we're talking about energy, we represent it as an energy. But then when we put it in an equation, all the charges on electrons cancel. Anyway, the voltage sub OX is the drop in potential energy between the metal and the oxide. And it has a 0 because this is when it's brought together without anything applied. So at thermal equilibrium is where we get that. And then on the other side, we have this drop in potential energy between the oxide and the semiconductor because we connected them together. And that was the thing that we were going to try to find, but we hadn't been able to find yet from the previous lecture. So at 0 bias, those are the values, and then if we add voltage or whatever, then they wouldn't have a zero attached, but they would still be the same type of value. So what we can do, and some of you have had circuit analysis and some of you haven't, but Kirchhoff's voltage law works in semiconductors too, and you can actually add the energy drops between the vacuum level and the Fermi level on both sides, and it should equal the same thing because of Kirchhoff's voltage law, basically. So what we're going to do is we're going to add the potential energy drops on the metal side. So we're going to go from the original vacuum level, which is the dashed line, and we have an energy drop across the oxide, and then we have the work function of the metal. So we can add those two together, and we get an equation. And that actually is, like I said, you could take the E's out, and then it will be in volts, but right now it's in joules, but we'll get rid of that in a minute. So that's one part. Then we're going to look at the other side. We're going to look at the semiconductor side. And you notice that there are several values that we can find there. We can find the chi value we can look up. We know the band gap of silicon. We can calculate the work function in the bulk material, phi sub Fp. But we have this weird work function at the surface, which we don't know yet, but that's okay. We won't worry about that because we didn't know the voltage across the oxide either. The problem is those voltages don't all go to the same place. It was easy on the metal side because we could just go and calculate one right after the other, but now we've got a voltage that drops to this point, and then we need to get kind of up here in order to go down to more. And then we have this value right here, but this is what we can do. We can actually do this and get to where we need to go. So what we're going to do is we're going to move this up. It is the same distance between that the conduction energy falls. It's the same as what happens in the intrinsic, so we can move that there. And then if we just flip it over and call it negative, we get to where we need to go. Because we go from the vacuum level and we drop E chi, which is the electron affinity. Then we go up this work function at the connection surface, and then we drop energies down to the Fermi level. So when we add them all up, we do have a negative sign for the work function at the connection surface between the bulk semiconductor and the oxide, and that's because we're using it as an energy rise in order to make the equation work out. So now that we've got this, we can actually set the two equations equal to each other because they should be equal. The distance between the vacuum level and the Fermi level should be the same. So we can actually set them equal to each other. And then we are, at this point, going to get rid of all the charges of an electron. Now you notice that the band gap energy is divided by 2E. But if the band gap energy were given in electron volts, one would not convert it to electron volts. So this is assuming the energy is still an energy. So it is really going to be used as a voltage. So what we want is the metal semiconductor work function, and that's equal to the total energy change in the system. So we can move things around a little bit. And basically those two values we didn't know, which really doesn't help much, but we didn't know the voltage across the oxide and we did not know the work function at the semiconductor oxide interface. But if you add those two together, that's the metal semiconductor work function that we want. And the cool thing is, because we had the equation above and we can rearrange it, we actually do get this equal to stuff that we can find. So we can actually calculate the value of the metal semiconductor work function if we just look up all these values. We can look up the doping concentration, the material of the metal in the semiconductor, and we can find that. And for an N-type material, it's almost exactly the same. It's not quite the same, but it's almost the same. So there is a way to calculate this. However, and this is a big however, those are ideal equations. And the problem is that there is something called Fermi level pinning that happens at the surface of a semiconductor. And the amount of it depends on the material that the semiconductor is made of. So Fermi level pinning occurs when there's a high surface density of charge carriers. And you know, in the bulk material, the doping concentration affects the Fermi level. But at the surface of the semiconductor, something different can happen in which you actually get a kind of a charge continuum between the conduction and valence bands. And what ends up happening is there is a point on that continuum in which the energy levels are closer to the conduction band above and closer to the valence band below. And we call that the charge neutrality point. And we have to have that, otherwise there will be charge where we don't want it. So basically the Fermi level is pinned to that value. It's pinned to that charge neutrality value because if it's above or below it, there will be electrons and holes accumulating on the surface and it wouldn't be charge neutral and it needs to be. So depending on the type of semiconductor used in the bulk material, it can have a big effect. For instance, gallium arsenide has a really high surface density of states. And so if you try to make a MOS device out of it, there is so much Fermi level pinning that the Fermi level is at a specific value and it doesn't matter what you do to the material or what you connect it to. It's always going to be the same. Silicon's not like that, but gallium arsenide is. But the upshot of this is that you can't really calculate phi sub ms directly and accurately from the ideal equations. But how do we know that those equations aren't correct? I mean, if you can calculate it, how would we really know that they weren't exactly correct? Well, the reason we know is because somebody actually went out and experimentally found these things. And we have a graph that can actually be very quick and easy rather than looking up all of the different values. There's a graph that actually gives the metal semiconductor work function for different types of doping concentrations. So for instance, for N-type silicon, if we wanted to pair that with aluminum with the doping concentration of 10 to the 16 per cubic centimeter, we would use this line right there. So that's aluminum N silicon. And then we would just go from the value of the doping concentration in the bulk, and we would read the value off that graph, and we get about negative 0.25 volts. If we went through and calculated it, and I'm not going to spend a whole lot of time on that because basically all of this is just running numbers through equations, you see that the value that I get at the end of 0.057 volts is not the same as negative 0.25 volts. It's actually just a little higher. So it's assuming that the work function difference is higher than it actually is. So we're going to look at a couple more. We're going to look at P-type silicon with gold. And when we go to that one and we have a doping concentration of 10 to the 15, we find the metal semiconductor work function is actually around 0. And if we calculate that using the values that we can look up, we get 0.242 volts, which is actually, again, almost a similar amount higher than it should be. So again, there's more energy somewhere that is not being accounted for. So you again get a value that's a little higher than what it actually is. And in the last, we have N-type silicon with a higher doping concentration, and that line's way up at the top. And if we look at that, we get a value of 0.7 volts. And that ends up giving us 0.937, which is, again, it's a similar amount too high when we calculate it by hand. So the actual error value is, at least in these examples, pretty constant. But if you calculate it by hand, you are going to get a value that's more than what you actually should get. So the good news is we can find the metal semiconductor work function. So we can actually find it. And what are we going to do with it? Well, this is what we're going to do with it. We need to know how to find two different parameters for the MOS capacitor. One of them is known as the flat band voltage, and the other is known as the threshold voltage. Now, this is a point of confusion for a lot of students because the threshold voltage V sub capital T is not the same as the thermal voltage V sub small t. V sub small t was a constant that we used repeatedly in calculations. V sub large T is a completely different thing, so don't get them confused because frequently students do. So anyway, flat band voltage. When you're at thermal equilibrium, you do have band bending that creates a space charge region, and you have a capacitance, which we have talked about. There are also charges that are trapped in the oxide, and the reason the charges get trapped is when this stuff is being made and during the oxidation process, sometimes there's silicon bonds that don't end up getting bonded to anything and they kind of dangle, and that creates charges that are trapped in the oxide. So that's a certain amount that actually is also a kind of a known thing, but we won't have to look it up generally. But the voltage drop across the oxide is directly related to the stored charge and inversely related to the capacitance. So that value, if we knew the stored charge, we could actually find that value and calculate it, although we don't necessarily know it. We sometimes do, we sometimes don't. But anyway, the flat band voltage is the voltage that counteracts this work function that's pushing the semiconductor bands down. So it basically counteracts the band bending. And we can say, remember we said that the metal semiconductor work function is equal to the negative voltage of the oxide plus that very work function at the surface between the semiconductor and the oxide. So we can move that around a little bit, and we can say that that semiconductor work function at the surface is equal to the metal semiconductor work function, which now we can find, and the voltage across the oxide, which again, we actually can find. So that is actually what the flat band voltage is equal to. And we could actually find that if we know the charge stored in the oxide, which, as I said, that actually is something that you can find out. So we could actually figure that out. So we have this situation in which we take the flat band voltage, and what we're wanting to do is we're wanting to push the Fermi energy down. And the things in red are the things that have to stay constant. And then we want the phi sub s to go away. So the distance between the Fermi energy and the intrinsic Fermi energy has to stay the same. And those three red points where the conduction, the intrinsic, and the valence energies are connected to the oxide, those also have to stay there. So what ends up happening is when that goes away, we end up moving the Fermi energy down, and the amount it's moved down is the flat band voltage. So the flat band voltage is pushing the energy down on the semiconductor side, keeping the work function in the bulk constant, but also retaining the places where the band bending ended up being connected to the oxide. So let's look at an example. If we have a MOS capacitor with a p-type silicon substrate, and it has an acceptor concentration of 10 to the 15, silicon dioxide as the insulator with a thickness of 20 nanometers, and we have an N plus polysilicon gate. And then we are making an assumption about the charge stored in the oxide, but we do know the relative permittivity of that. So we're going to find the flat band voltage. So the first thing we do is we find the oxide capacitance, and when we do that, we calculate, remember you have to use the relative permittivity and the permittivity of free space, so that's why the permittivity value has two numbers. Then we put in the oxide. Remember that the oxide is being put in centimeters. That's why it's not 20 times 10 to the minus 9. That's why it's 20 times 10 to the minus 7, because we're finding the oxide capacitance per square centimeter. So that's why. And when we do that, we get 1.726 times 10 to the minus 7 farads per square centimeter. So we're going to push that up, and then we're going to use the graph to find the work function of the metal semiconductor connection, and we find the line for it is way down at the bottom, and we go to the concentration and then move over, and we can actually find the value of the metal semiconductor value of about minus 1.1 volts. And now that we know everything, we just plug the numbers in. So we knew the charge in the oxide, we calculated the capacitance, and we know the metal semiconductor value, and we get minus 1.15 volts for the flat band voltage. So that's how we find that. We're going to need to find it again in the next section, but that's what we do when we want to eliminate all the band bending. We actually have to apply a voltage in order to push the bands down. The next thing we're going to find is the threshold voltage. The threshold voltage is what needs to be applied in order to get to that threshold inversion point, which is going to be important when we're talking about MOSFETs. So the threshold inversion point, remember, occurs when the work function at the semiconductor oxide junction is equal to twice that of the bulk material, and that's good for P-type and N-type material. And then when we look at the voltage applied at the gate of a MOS device, it's a combination of three different potential drops. It's the voltage across the oxide plus the work function at the surface between the oxide and the semiconductor, and then the work function difference between the metal and the semiconductor. And we can actually look at that at the threshold voltage, and when we do that and we substitute in the threshold voltage, we have Vox T, and that means whatever that voltage is at the threshold value. And then we have 2 times the work function of the bulk material, which we can calculate, and then the metal semiconductor value, which we can also calculate. So how are we going to find that value, that oxidation drop? How are we going to find that? Well, what we're going to have to do is look at the charge distribution of the MOS capacitor, and we're going to be able to figure it out. The potential drop is going to be equal to the charge in the metal divided by the capacitance across the oxide. And we don't know how to find that. Well, we're going to know how to find that, but right now we don't know how to find that. So we're going to figure out how to find it. So when we look at how charge is distributed, the green rectangles basically are showing you how much charge there is in a very idealized fashion at these interface junctions. So this would be the metal to the oxide, and this would be the oxide to the semiconductor. So there is a lot of charge here, but then there isn't any out here. So the charge is basically at the surface of both of these at this junction. And then there's going to be charge stored in the semiconductor, and that's going to be stored down here. And we can assume that the charge in the metal and the oxide are going to equal the charge in the semiconductor. And we know how to calculate the charge in the semiconductor because we already did that. We did that before, and we found that was equal to the acceptors times the distance of the space charge region, and that distance of the space charge region is what extends into the semiconductor. So this is kind of stuff that we've touched on before. So that way we can get the charge stored in the metal at the threshold inversion point as long as we can calculate the value in the bulk semiconductor material, which is Q prime SD max, we can do that. And as long as we know the value of the charge stored in the oxide. And that means that the potential, now that we know that the charge stored in the metal is equal to the total charge in the semiconductor minus that in the oxide, we're getting closer to being able to figure out what this value is. So we can look at the threshold voltage and represent it now that we put the oxide voltage back into the original equation. And then remember that the flat band voltage was the metal semiconductor work function minus the charge stored divided by the capacitance per unit area. So we can actually substitute that in if we wanted to, and we get the threshold voltage is equal to the charge in the semiconductor material divided by the capacitance per unit area in the oxide plus the flat band voltage plus 2 times the work function in the bulk material. So if we apply a voltage, that pushes the Fermi energy down on the metal side and creates conditions for inversion. So that's the threshold voltage right there. That's pushing the Fermi energy in the metal down. We have the values on here that we can calculate. So the threshold voltage is a combination of the values of charge that we can calculate, the capacitance we can calculate. The flat band voltage, remember, brings us from the vacuum level down to the Fermi level. And then on the other side, we have that drop due to the bulk work function. And when we have that all put together, we can actually find the values that we need. So we've got the same MOS capacitor we had before. So you may not remember because it's probably been 10 or 15 minutes since we did this example before, but this is exactly the same value that we use for the flat band voltage. So we already found that. We found the capacitance and the flat band voltage already, and we can find the value of the work function in the bulk material by just calculating the thermal voltage. Remember, V sub little t is thermal voltage of 0.0259 times the natural log of 10 to the 15 over 1.5 times 10 to the 10, and we get 0.288 volts. Then all we do is plug in numbers. We plug in the values to the distance between the oxide and the area where the band bending stops. That's the depletion region, and we get 0.863 times 10 to the minus 4 centimeters. And then we can calculate the charge just using the charge of an electron and the concentration, the acceptor concentration we had given before, and the calculated width that we found, and we get 1.381 times 10 to the minus 8 coulombs per square centimeter. And then we put all that in the threshold voltage calculation, and we end up with minus 0.494 volts for the threshold voltage for this particular value. So this does depend on us being able to find the flat band voltage or calculate it, and we can actually relatively easily look up the charge for some of the values. There are tables where you can go look up the standard amount of charge that's stored in the oxide. So it actually is possible to look that value up and get a pretty reasonable value for that. And this is basically a summary of all the things that go into finding the threshold voltage. So remember, we have to find the work function of the material in the bulk. We have to find the capacitance per square centimeter. We find the flat band voltage, or we need to know the charge in the oxide, which we can look up on a table, and we can look the metal semiconductor work function also on a table. And we need the width of the work function, and then finally we can find the charge stored in the semiconductor.